Today's show is brought to you by ExpressVPN. Protect your online activity today and find out how you can get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Visit tryexpressvpn.com/space to learn more.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello, and thank you for joining us on the Space Nuts podcast. My name's Andrew Dunkley, your host, and joining me, as always, Professor Fred Watson, astronomer at large. Hello, Fred.
Good day, Andrew.
How are you, sir?
Yeah, I'm all right, thanks. Good to talk to you. And,
you too, as always.
Yes, I'm well.
Now, we've got a fair bit on today. We're going to try and tackle a few questions a little later about the Big Rip, wormholes, and an interesting sort of local one about Wi-Fi interference from satellite internet in regard to the square kilometre array. That's a really interesting question because they're all over each other, really. But first, we're going to talk about the oldest star in the known universe that may have been discovered. So that is exciting. And long-haul space travel may be impossible because of brain damage. Now, I'm assuming the brain damage happens after the long-haul travel has started, or we are suffering brain damage because we're thinking of going. I'm not sure which, but we'll get to that a little later. First of all, Fred, this ancient star could be the oldest one ever discovered.
Yes, that's right. There's something of a race going on with this in the world of astronomy, and Australia does pretty well at it, actually. So I can remember back in the 1980s when, almost every week it seemed we discovered a more distant object. They were usually quasars. And so the record for the most distant object known to humankind kept tumbling. And it's a little bit like that with the oldest star. We see these things come up, and then a few months later, there's another one that's even older.
It's Mick Jagger, by the way.
I know a few that are older than that. Just to clarify, we will one day be able to see. Well, let me start that again. When we look deep into the sky, as you know, and all our listeners know, most of them anyway, you're always looking back in time. And so you can imagine a situation where you're going to be looking back at really ancient galaxies. And in fact, there are some in which you can see individual stars because of things like gravitational lensing, which means that you are seeing stars very early in the history of the universe. But what we're talking about here is not that. It's not the looking back in time trick. Or trip, whichever way you like it. It's not the looking back in time trick. It is the ability to see stars in our neighborhood, which have evidence of being very ancient. And the way you pick that out is initially it's by a star having strange colors. And that's how the Australian, it's actually called the Sky Mapper telescope, run by the Australian National University at Siding Spring Observatory near Coonabarabran. Sky Mapper is great for doing that because it's got a whole array of filters, and it can take images of the sky, really detailed images of the sky, looking through these different filters. And that allows scientists to say, well, here's a candidate for an old star. But that's not enough. What you then have to do is go and follow it up with a bigger telescope, one that will allow you to look at the spectrum of the star, the rainbow spectrum, and to see this barcode of information that's superimposed on the spectrum. And a barcode's a really good analogy because when we look at the spectrum of a star, it's exactly what we see. And the black lines on the barcode equate to what we call absorption lines. They're essentially the fingerprints of different elements in the star's atmosphere. So the most abundant element in the atmospheres of stars is hydrogen, because that's what the universe started off as. And what happened in the very early universe, there was nothing else. Actually, there was helium as well, but hydrogen and helium were the only things substantially that were there in the early universe. There were trace elements of a couple of other things, but that's not important in this context. And the first generation of stars, the earliest ones to form, would have basically not much more than hydrogen in their spectrum, probably a bit of helium, because it was in the interiors of those stars that the other elements formed. The silicon, the oxygen, the carbon, the iron, all of those things are formed inside stars. And that first generation of stars would give rise to some of these heavier elements. And then, because we believe the first generation of stars were very massive, they lived for short lives, measured in tens of millions of years rather than billions of years like our sun. Those massive stars would all have ended in a supernova explosion, which blows the debris from which they are made, or at least the atmosphere, the debris from which the atmosphere is made, out into the wild blue yonder, which in this case means the interstellar medium, the space between the stars. And what that does is then provides raw materials for subsequent generations of stars to form.
I was going to ask if they feed upon themselves and recreate accordingly.
So each generation of stars builds on what went before it, and their atmospheres are enriched by all these atoms that have been created in the previous generations of stars. So if you want to find a very old star, what you need to look for is something that's got very little in it other than hydrogen and helium, very little in its spectrum. And that's basically what has happened with this particular star. I've got to tell you what it's called.
Oh,
Andrew.
please.
This one's a cracker. J160540.18 minus 144323.1. And I forgot that its prefix is SMSS,
So
which I think...
I've got to say it again because it's just so cool.
No. Say it again. No. But SMSS... and all the rest of it. SMSS, I think, just stands for Sky Mapper Sky Survey, probably.
Yep.
So that's basically what we've got. And that particular star, whose name I'm not going to say again, turns out to have virtually nothing in it other than hydrogen and helium. The one thing that is in it, which is a kind of gauge as to how old it is, and this is really the yardstick by which these old stars are judged. What is in it is iron, and iron content is a measure of how early a star has appeared in the history of the universe. This one has an iron content of 1 part per 50 billion, so it's very, very sparse in iron. In fact, some people are describing it as anemic, which is a very nice term.
Yes.
That means iron deficiency. It's a very anemic star, and its iron content is a record low. That's the bottom line. So that's what the published paper will say. It's got. In fact, they describe them as ultra metal poor. These stars. And a metal, by the way, to an astronomer is everything except hydrogen and helium. I know that sounds bizarre, but we think of, even oxygen and carbon and things like that as metals, but it's not a metal in the normal sense of the word. That aside, this star is very, very poor in iron, and that places it in the record books as being, at the moment, the oldest known star. But watch this space, because in a couple of months there'll be another one that's even older.
I suppose. So where is it? Can we point at it?
It's actually, yes, it's in the Milky Way galaxy. It's actually in the halo of our galaxy. That means that not the disk of the galaxy, but there is a spherical, fairly rarefied distribution of stars around the galaxy. We call it the halo, and that's where it is. It's about 35,000 light years away as the crow flies, so a rather distant object, but still in our galaxy, and of great interest because its iron content is so low.
Yeah.
A nice comment from I think it's the lead author, actually, Thomas Nordlander, who's from, I think he's from the Australian National University. He has this lovely quotation, which is that amount of iron, one part in 50 billion, it's like one drop of water in an Olympic swimming pool. Not a glass of water, but one drop of water in an Olympic swimming pool.
Wow, yeah, it certainly is an anemic star. Of course, there are probably others out there. This one's in our own system, but could there be older ones in other galaxies that we may never be able to catch on to?
Yes, that's true. I mean, I guess we could look for these things also in, in our nearest neighbor galaxies, like the Andromeda Galaxy. It is possible that when we get to the next generation of big telescopes, the ELTs, the extremely large telescopes, we will find that we can image the stars in our nearby galaxies to the extent that we can do the same sort of measurements on them. And you can bet your life that there'll be really ancient stars in there as well. These stars are, they're stars that are relatively small compared with the giants in the early universe. And so they've been very sparse with burning up their hydrogen fuel, and that's why they're still going strong after probably 13 billion years or so.
Gee, that's a long time, isn't it? I mean,
it is, yeah. It is a long
hard to
time.
get your head around a star being in existence for that long. But then again, the universe has been in existence for longer. So, yeah, why are we surprised? So that's the story of J160540.18 minus 144.323.1. You knew I was going to do it.
Yeah, I did, yeah. So sadly, it's not one of the first generation of stars, but it probably belongs to the second generation, the ones that were formed from the debris of the first generations.
Very good. Fascinating. All right. But watch this space, as Fred says, because we'll probably tell you about an older one in a couple of weeks' time. You're listening to Space Nuts. Andrew Dunkley here with Fred Watson. Now, let's take a little break and find out more about our sponsor, ExpressVPN, rated #1 by Tech Radar. This is the one I use. I've been using it for a couple of years and I love it. When I joined ExpressVPN, they were brand new to the market, but I read a lot of reviews and did a lot of comparisons. And there was just something about their business model that I particularly liked. And a couple of years down the track, honestly, can't complain. Their interface is very easy to use. Their service is second to none. I've had to contact them a couple of times about certain things that I wanted to do, and they were brilliant. So you may be wondering why I do need a VPN at all. It's all about privacy. Do you really want big tech companies, governments and others knowing what's going on with your online activity? Even if you're having nothing to hide, it just feels downright creepy. I think you'll agree. And governments are getting more and more interested in what you're doing every day. And so, yeah, protecting your privacy is what VPN is all about. And how often do you run across websites that you want to get information from only to find that they're geo-blocked? This is becoming an increasing problem, but ExpressVPN solves that problem for you. Now, if you go to our special URL, you'll see quite a list of things this service can help you with, things you may never have thought of before. As I say, it's the one I use, secure, fast, and it just works. So protect yourself online today and find out more about how to get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Try expressvpn.com/space to learn more, and you'll find the link details in the show notes and on our website. Now, back to the show.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Now, Fred, a lot of people have asked us about long-haul travel, and we're going to actually tackle one of those kinds of questions a little later. How can we do this? We talked the other day about long-haul travel in space using perhaps solar sails. But the reality of sending people long distance versus a small spacecraft is a very, very different venture. And we certainly don't have the technology to fold space, which is certainly something that has been considered in the realm of science fiction. So if we're going to send people long distance, we're going to have to do it the old-fashioned way. And now it's starting to look like that might be more difficult than we first thought.
Yes, that's right. I mean, I think it's fair to say that of the technological problems that face us in terms of getting people, for example, to Mars, the radiation issue is perhaps the most difficult to solve. You can provide your astronauts with an atmosphere. You can probably even build a spacecraft that will mimic the Earth's gravity by rotation, by centrifugal force, all of those things. But what you can't do very easily without lots of shielding is stop the subatomic particles getting through the skin of the spacecraft. And in particular, it pertains to long-haul spaceflight, exactly as you say. So just looking at what we've done in human spaceflight so far, most of the experience of astronauts and the medicine that's been done with astronauts relate to scientists either in the International Space Station or its predecessors like Mir and Apollo-Soyuz and things like that. Those are long duration space flight, but they're very much in the local environment. And all of those astronauts are protected to a large extent by the magnetosphere of the Earth, basically the magnetic shield that the Earth's magnetism builds around the planet. So certainly the International Space Station is well within that zone. Travel to the moon, of course, meant astronauts left that protective zone around the Earth, but their duration was not that much more than a week of the order of 7 to 10 days. And that means that their dosages of the subatomic particles were relatively low. And so we don't have any direct experience of plonking people out there in the middle of nowhere and watch what happens when they're radiated by two specific sources. One is the solar wind, this wind of subatomic particles, basically electrons, protons and electrons from the sun. But the other, and really maybe more dangerous one, is the what's called the cosmic ray flux. So cosmic rays actually come from our galaxy and other galaxies. They're not from the sun itself. They're a background of subatomic particles that come from sources actually that are not that well defined. They are within our galaxy. There's probably a lot of stuff that results from neutron stars, stuff that results from perhaps black holes, from supernovae. All of that stuff is floating around, and we are irradiated with it. Actually, cosmic rays I think they were first measured before the First World War by scientists using balloons to see, to record what happened. So the cosmic ray flux, and particularly the high energy cosmic ray flux, is something that we, I guess, have recognized for quite a long time as putting long-haul astronauts at risk. But now, some work that's been done by scientists, actually they're both, the two scientists who published this work, they're both at University of California, Irvine, and they're both basically involved with radiation oncology. That's their specialism. And it's work that they have done in looking at relatively low doses, the kind of things that you might find irradiate astronauts traveling to Mars, but over long periods of time. And of course, they haven't used astronauts; they've used mice as basically as substitutes.
As you do.
As you do. So they did this for 6 months. They basically exposed mice to low-level neutron radiation for 6 months, and then looked at the neurons in their brains. In particular, these are the cells that essentially store memories and things of that sort.
And they concluded it's not a tumor.
Well, they concluded that they don't work very well anymore. Yeah. The fine structure in the neurons has been damaged, and maybe some of the connections have as well.
Oh.
So there were clearly in the their studies, of course, after the irradiation, they tested the mice to find out in behavioral terms how they were coping, and they say the outcome of our behavior studies demonstrated that mice exposed to neutrons for 6 months had trouble with learning, adapting, and storing memories. For example, these mice were less likely to be interested in a new toy that had been placed in their testing arena compared with a toy that they had already seen before. The control mice, on the other hand, would take much more time to explore the new toy than the old toy. And similar tests. But what was also really interesting is that the irradiated mice demonstrated social problems, much more likely to avoid social interactions, had difficulty dissociating or forgetting an adverse event that happened in the past. The space radiation induced changes that increased anxiety levels. So they essentially believe that they've replicated what would happen to a human brain in space. And they believe that this could significantly impair, once again quoting their work, could significantly impair the ability of astronauts to respond under stress or in unexpected situations. And what they've done, they kind of, translate those findings into what that might mean in human terms. And they say, we estimate that in a crew of 5 astronauts traveling to Mars and back, we would expect at least one member to display severe deficits in cognitive function by the time they return to Earth.
That is scary.
Yeah, it's very scary.
I mean, it could be all of them, couldn't it? It's statistically, it 1 in 5, but it could actually go the other way.
Yeah, that's right. They qualify their work by saying, this is just one study and the results must be replicated, but it does raise the sobering possibility that galactic cosmic radiation exposure may represent a significant obstacle to deep space travel.
And once again, I call on science fiction to provide the answer. And in the movie Signs, they wrap their heads in aluminium foil.
Oh,
I think that there it is.
Why didn't they think of that? Why didn't these guys just think of that? If you want to follow up on this, it's on the US edition of the Conversation. Astronauts' brains are subject to long-lasting damage due to low dose.
The Conversation website is one of the best online facilities for really getting down and dirty into some deep and meaningful stuff. I go to their website so often because there's always something interesting, and they really do a great in-depth analysis. It's fantastic.
Absolutely. I agree with that wholeheartedly.
Because you actually answered 2 or 3 questions that were formulating in my mind while you were talking, because I was going to say, we're protected by the magnetosphere. We don't go out beyond it much except to go to the moon and back, and we were only out there a week. So why haven't we tested a long-haul trip, sending someone out for a month and then coming back over, so it's a 2-month trip just to see what it's like? Probably a good thing we didn't.
Yeah, I think that's right. That's the bottom line.
So that's another problem we need to solve.
Yeah. I mean, I think, you just have to send them up there with some aluminium. That's aluminium foil.
Yeah, got to wrap that stuff around you. It is, good for heat dispersion as well. Sorry?
Which movie was that?
That was in the movie Signs. They wore these silly little aluminium hats so that the aliens couldn't read their minds.
Oh, that's it. Yeah.
Yeah. But, it'll protect you from all that other stuff as well.
Sure, that's right.
Very good. Except don't put it in a microwave oven, I guess. All right. And I might mention, and please forgive me for forgetting your name, but we got a message on Facebook the other day from someone who is looking at becoming a doctor, but specialising in space, and wanted us to actually talk about some of the afflictions that astronauts might face. So she'll be fascinated to have heard that particular problem. Yeah. That's a new problem, but there are many others, like the issue with damage to the eyes, and of course muscle wastage is a big issue as well. It's just the list is rather long, isn't it, Fred?
It is. Space medicine is alive and well. It's a career that I think is burgeoning in the space world. It's probably pretty competitive to get into, but it's very, very interesting, the research that's being done today, including things like this.
Well worth pursuing, because they're going to need people going forward, because this is just going to get bigger and bigger, I imagine. Okay, you're listening to the Space Nuts podcast with the nutty professor, Fred Watson, and the even nuttier Andrew Dunkley.
3, 2, 1.
Space Nuts.
Now, Fred, to the question whiteboard, which is where we put all our questions, except it's virtual. We're going to try and tackle a few today, and hopefully get through them without severe interruption from one Mandu the cat, who is in your presence right now. So hopefully you'll say hello. But anyway, we'll carry on. It's not like grandchildren walking in on you, I'll tell you that much. Now, our first question comes from Wes Smith. Hi, Wes. If the universe is infinite, or we really don't know how big it is, how can we categorically say there's not enough matter for a big crunch? With the discovery of new galaxies, black holes, etc., and that we don't completely understand dark energy or dark matter for that matter, who's to say that the universe won't stop expanding and reverse itself at some point? Respectfully, Wes Smith. Now, we have kind of touched on this before, but it is worth sort of looking into that potential crunch. I mean, when I was a kid, that was the belief that the universe would expand like a rubber balloon and reach a point where it'll go, oh, and crash back in on itself. And I thought it was going to happen the next day. But but now we think it's not going to do that at all. But there are, obviously people like Wes who wonder why it won't.
Well, it's a great thing to ask. Let me just I can't resist saying this, and I think we've said this before, but Brian Schmidt, who was one of the co-discoverers of dark energy, the accelerated expansion of the universe, he always used to refer to the Big Crunch as the Gnab Gib, which is the Big Bang backwards. So the Gnab Gib is the end of the universe.
Never gets boring, that one.
No, it's a good one. But look, Wes is right on the money. And we can't say categorically that there is not enough matter for a big crunch, because all we can say is that as we look within the observable universe now, the expansion is accelerating. There are horizons to the universe beyond which we can't see, and things like the cosmic microwave background radiation. That's one of them.
And dirt.
There's stuff like that as well. But there are fundamental reasons why we can't see the whole universe, and indeed we don't know whether there is a whole universe. It may be infinite, as Wes suggests. One of the things that has been suggested is that what we see in our accelerated expansion is just one little blob of a much, much bigger universe, which is, some bits of it which are in a state of expansion, some are probably in a state of slowing down expansion as distinct from our accelerating expansion. But we can't detect those. And so you've got to, whenever you make a statement about what the universe might do, you've got to build all these caveats into it. The evidence at the moment is that certainly as far as the bit of the universe we can observe is concerned, it is expanding more rapidly than it was 5 billion years ago. So that's all we can say. We can't rule out a big crunch because for, exactly the reasons that Wes has suggested. So
we can't rule out a big pop either.
No, we can't, or a big rip or whatever. Look, it's why scientists, particularly cosmologists, they sometimes sound wishy-washy, because you're saying, well, the best information we have at the moment is this, this, and this. But that really is all you can say. You can't say anything categorically about a big crunch.
But as it stands, what we're seeing is the expansion is ongoing and accelerating.
That's correct. Yeah.
So that's what we know definitively, but we don't know categorically.
Now a bit of the universe.
What will happen next.
Yeah, we don't know what will happen next.
Yes. All right. So there you are, Wes. Hopefully that will help you sleep at night. Now, moving right along, I've been wondering a lot about how humans will travel to other solar systems. Well, they won't have brains, so it won't matter. And I know that the regular rocket way won't cut it. It would take thousands of years to get out. I've heard people talk about wormholes, and it all seems kind of odd, the whole idea. My question to you is there any scientific backing that wormholes exist? And if there is it a possible means of transportation as our technology gets better in the next few hundred or thousand years? Sincerely, Weston Myers, Oregon, USA. Thanks, Weston. Wormholes.
Yeah, no, they're a theoretical entity, but they come completely without any evidence of a practical nature. So in the 70s, when people were looking at the physics of black holes, it was realized that you could actually, in the equations, you can just reverse the sign of time. If you've got negative time, the physics all seems to work, and you end up with white holes rather than black holes. And then the suggestion was made that if you got, two of these things back to back, whether they were white holes or black holes, you might form a wormhole, which might essentially link unrelated parts of the universe. But there's no observational evidence whatsoever for this. And even if there was, the extremities of gravitational distortion that you get anywhere near a black hole are such that it's very hard to see any technology in the next 10,000 years probably that could overcome that. So my guess is that we are stuck with conventional methods. They might, however, allow us to do interstellar travel more rapidly than the current regime of chemical rockets, which really mean that for the nearest star, you're talking about 60,000 years or so. But if you can augment that with light sail technology, and there are certainly projects looking at that, including one that we spoke about last week. And by the way, that reminds me, we were going to add what the big news item was about that.
Yeah, I did put it on Facebook, and I must confess, I was a little bit of, my reaction was a bit, because all they were announcing was that they did it and it worked.
Yeah, they did it and it worked, but they actually managed to steer it, and in fact to put the spacecraft into a higher orbit, which it is quite big news, isn't it?
Yeah, it is. It is.
It's possible that.
Hello, Mandu.
Yeah, he's being naughty. Actually, he's kind of having a go at the furniture. He's just a bad lad, Anyway, so light sail technology is promising in terms of, certainly with small spacecraft, accelerating things to a significant fraction of the speed of light. And so there is this project called Breakthrough Starshot, which is an initiative by this Russian billionaire, Yuri Milner, funded by Yuri Milner, which is to look at the possibilities of sending a very small spacecraft, and by small I mean a centimetre or thereabouts, to the nearest star, Proxima Centauri, with a light sail powered by lasers either on the Earth or in the vicinity of the Earth. That's all they're doing at the moment is looking at the feasibility of it. And I haven't seen a final report on that, but you can tell that people are thinking of these ideas. So it may be that there are technologies that we can employ, but wormholes doesn't look like one at the moment.
What about folding space?
In a sense, it's related to wormholes. So there was a paper which I read, is probably about 20 or 30 years ago now, which was published, I think, in a UK astronomical journal, where somebody looked at the physics of the warp drive in Star Trek, which involves folded space, and very quickly arrived at the conclusion that you need more than the entire energy budget of the universe to make it work. So everybody kind of lost interest after that, which is fair enough too.
Understandable. Okay. So probably not Western, unfortunately. Not at this stage. They might find something else. Now, to our final question today. Hi, Andrew and Fred. Oh, I got to go first. Woohoo!
Obviously not Dave this time.
Not Dave this time. A first-time emailer but long-time listener. While reading one of the regular manufacturing monthly newsletters, oh, how exciting, I came across a story about a Western Australian Minister for Regional Development, Alana McTiernan, switching on the national broadband network in Australia, Western Australia's Midwest. Now, for those who don't know, the national broadband network is our high-speed internet service. And in some areas in remote country, it has to be fed by wireless signal. I presume the Midwest, this includes areas just south of the region encompassing the square kilometre array and other radio astronomy projects. So that raised some questions in relation to the technologies used for the wireless broadband network, which bring advanced technologies to remote farmers. Given the SKA is so sensitive, isn't putting powerful wireless base stations 100 or 200 kilometres away potentially a risk? How close is too close? How big is the safe zone for $1 billion international project? How does the SKA deal with noise from such fixed sources? Is there a no-fly zone for drones and other industrial or agricultural aircraft that are mobile sources of RF noise? Are dogs and cats living together? Who shot JR? I'm keen to hear your thoughts.
And that's from Justin in Melbourne.
That's from Justin in Melbourne. Thank you, Justin.
That's a fantastic question, and it is right on the money. And I think Justin sounds as though he's got some handle on the technology, so I can direct him straight to the horse's mouth if I can, which is the web page which relates exactly to this. There is a web page on our website. That's the Department of Industry, Innovation and Science. One of their web pages is called the Australian Radio Quiet Zone WA. And that is all about essentially the exclusion zone for radio frequency interference in the square kilometre array. And it's quite extensive. That website actually gives details of not just the area that's covered, which actually is more than 500 kilometres in diameter. It's a large area centred on a point which is about 350 kilometres northeast of Geraldton, which is the radio quiet zone. And that is actually covered by a whole lot of legislative, regulatory and policy instruments that actually set up the legalities of what you can and can't do there. So they include things like the Midwest Radio Quiet Zone Frequency Band Plan, and that's telling you what frequencies you can operate on. The assignment and licensing instructions, I think that's all part of the structure. But in particular, there are things like the radio communications class licenses for satellite phones, CB radios and low interference potential devices, as well as radio telescope mineral resource management area. All of these things are already in place. That's in the inner zone, which is out to 70 kilometres. There is an outer zone beyond that to 150 kilometres, and then there's something called the coordination zones, which go out to 260 kilometres radius. So you're talking about 500 kilometres all told. I had a quick look at all these when this question came up, and of course the thing about radio transmissions that are used for communications and things like that, they're at very specific frequencies. There are big gaps in those frequency bands, which are the ones that are of interest to radio astronomers, and that's why these things sort of interleave with one another. I know from talking to astronomers at the Murchison Radio Astronomy Observatory that one of the problems that they have, notwithstanding all this stuff, is that their telescopes are so sensitive that they get radio interference from reflections from the moon.
Oh, my word.
So if you've got communication signals which are thousands of kilometres from the telescope, they are still effectively finding their way to the telescope because of reflection from the moon. So it is a very difficult issue. It's kind of similar, to the problems we have in optical astronomy, where we're looking
at light pollution.
Yeah, but my suggestion is that Justin actually goes and has a look at that website because the details are there, and in particular how it interacts with things like high-speed broadband and the NBN.
What about the no-fly zones and drones and planes?
Yeah, it's all in place as well.
Yeah, so it's all covered. It's all covered, Justin. It doesn't mean it will stop stuff from getting through, as we've discussed, but at least they've come up with a formula that will reduce the amount of interference and enable them to find the little green men or whatever else is out there in the long term. In answer to Justin's other question, it was Kristen Shepherd who shot JR. He didn't ask that question. I just threw that
Justin,
in.
I hope you'll, just humour Andrew. He gets like this from time to time.
Happens after I've spent a lot of time in space for some reason. Yeah.
That could be it.
That'd be it.
That's right.
Probably a lot of time in the space between my ears. One more thing before we go, Fred. We have to shout out to our patrons again. Fantastic people, and the numbers are growing. We now have 33 patrons who are supporting our podcast, and we really appreciate them putting up a few dollars each month to keep us on the national broadband network because it's so darn expensive. But fantastic. Thank you. And don't forget to follow us on Facebook. We put a lot of information on our Facebook page. So do a search for the Space Nuts podcast on Facebook and follow us and like our stuff and share it with your friends. That would be fantastic. Get the word out and get a bigger and bigger audience because it's good for my ego, I think. Fred, as always, it's fantastic, great fun, and look forward to talking to you again very, very soon.
Sounds great, Andrew. Thank you, and have a good week. Speak soon.
You too. Fred Watson, astronomer at large, and thank you for your company again this week, and we will join you next time on another edition of Space Nuts.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes and Stitcher or your favourite podcast distributor. This has been another quality podcast production from Bytes.com.